And I will ask if anybody has questions for the speakers, please send them to me, Ivone Albuquerque. And if there's technical questions, please send it to Tiago. You can see his name, Tiago Godinhoto. It has ICTP, so he will be able to help you guys. Any other information, Fabio, Enrico? I think that's all, right?
I think that's all.
I think that's all. The usual request to please stay within the times. We would be happy to give you 10 minutes more each, but we can't. It's really...
Yes, exactly. So I'm going to be, strict. So, okay. So our first talk will be by Tim Wolf on latest results from the Xenon 1-ton detector. Welcome, and you can start.
Hi, can you hear me first, maybe?
Yes, we can hear you. Maybe.
Excellent.
Yes, okay.
So my name is Tim Wolf. I work at MPI K, and today I would like to talk to you about the latest results from Xenon 1-ton detector. So first, I will talk about the Xenon 1-ton experiment. So Xenon 1-ton is a time projection chamber, which was operated underground at INFN's Laboratori Nazionale del Gran Sasso, short LNGS. And here on the right-hand side, you see a photo of the facility underground where the magic is happening in the end. Xenon is currently the world's most sensitive dark matter experiment for WIMP searches. Here you see a picture of the Xenon family of all the institutions belonging to Xenon, and it's more than 170 scientists from all across the globe. As you know, we are also affected by this ongoing pandemic, and this meant that our last technical meeting in May had to be virtually in Zoom, and here you see our collaboration photo at the time. So now let's dive into physics with TPCs and with Liquid Xenon. Here in the right-hand side, you see a sketch of the TPC. You see Liquid Xenon in the center, and as entering the TPC, prompt scintillation photons are liberated. These photons can be detected at the top and at the bottom with photomultiplier tubes. There are two arrays at the top and the bottom, and this allows us to detect these photons. But not only photons are liberated in the detection site, but also electrons. And since we have a drift field, these electrons are drifting upwards in the TPC. Once they reach the liquid-gas interface, they also feel the extraction field. And then these electrons travel through the gas, electroluminescence happens, and again, photons are liberated. These are detected then again with the PMTs at the top and at the bottom. What you see here at the top is sort of the hit pattern, which allows us to localize the XY position of this interaction. We can also reconstruct the depth where this interaction happens, and this we do by the time difference between this S1 and the S2 signals. So this allows us a three-dimensional position reconstruction. After having done some calibration of the detector, we can also reconstruct the energy which is deposited per event. And this we do essentially by using this S1 and this S2 signal, and this allows us to get an energy estimate. In order to operate the TPC, we need very low backgrounds, a very low energy threshold, and a large exposure. So this is why these experiments are so large and so big. I'm mentioning here also that we try to discriminate the interaction type. So if it's an electronic recoil or nuclear recoil. Here on the right-hand side, I show you exactly now this plot in S1 on the x-axis and S2 on the y-axis for calibration data, so where we know the behavior that we would expect. And what you see is that the nuclear recoil data lies below the electronic recoil data. So the ratio of S1 and S2 allows us to discriminate between electronic recoil and nuclear recoil data. What you see here now is science data from Xenon 1-ton, and this is in principle what you know Xenon for. So for WIMP searches with nuclear recoil data. So in contrast to the previous slide, here much fewer events, just because it's science data now. And you see here again S1 versus S2. What you see on the right-hand side of the plot is the R squared versus the S2. So where in the TPC the interaction happens, and this you see also that there are some wall backgrounds which we're able to control here. Okay, and what you usually do, or what we usually do, is we take this data that I briefly present you here, and we put it into limits on the WIMP mass versus the WIMP nucleon cross-section. So per WIMP mass, we are setting limits on the interaction cross-section for the WIMPs. And here you see our money plot at the moment, where we set the most stringent limits down to a mass of 3 GeV. So here, this plot you've already seen, where I'm pointed you towards this red region for the nuclear recoil data. But now we are switching gears, and we are looking at this upper part here at the electronic recoil data. So this electronic recoil data, we are able, as I mentioned, per point in this S1 versus S2 space, we can associate energy with it. And this we can do because we have calibration data which characterize our detector. And this then allows us to essentially look at the energy which is deposited in the detector. So in the end, we will not look at S1 versus S2, but we will look at this combined energy that we have here. And in order to reliably or meaningfully run Xenon, we need a large exposure, energy threshold for the electronic recoils about 1 keV, and an ultra low background of less than 100 events per ton per year per keV in the electronic recoil case. So now I would like to give you a flavor of the science program of Xenon. I briefly touched upon the WIMPs. We also have analyses about double electron capture and other rich physics analyses which are ongoing. Today I would like to give you a flavor of what we did regarding solar axions and neutrino magnetic moments. However, in order to go that step and tell you something about these physics topics, we need first to have, let's say, a walk through how we do analysis in Xenon. We first need to do a data selection. We need to define what we expect. We do this by a background model. We need to do statistical inference, and we need then to show our results essentially. So let's start with the data selection. We apply standard data quality cuts to clean our data. And here on the right-hand side, you see the Z, the depth of the TPC, and the R squared, which shows you where in the TPCs the events which we are recording happen. And this led us to the decision that we choose this red box here, which corresponds to a 1 ton fiducial volume, where we only take into account events inside this volume. So this reduces by a lot the backgrounds that we are having from materials, for example. And then we are looking into single scatter events for this electronic recoil event that I was mentioning in this band. And we are setting an energy range between 1 and 210 keV. We are looking at data between February 2017 and February 2018, and this we denote as Science Run 1. So if I'm mentioning Science Run 1 quite more often, this is what it means. So next, we need to develop some kind of background model. What do we expect from our detector? What do we expect to see? In order to define that, we take into account several internal backgrounds. For example, this lead-214 background, which stems from the radon-222 decay chain, which is essentially for low energy is the dominant contribution. We're taking other backgrounds as well into account, and also activated backgrounds, because I'm not telling you the full story here, because the full story is that we are actually taking into account time periods which happen directly after neutron calibration. We treat them differently as time periods which happened far away from neutron calibrations. And we also take into account contaminant background and materials. And here in the center of the slide, you see on the x-axis, indeed now this energy range that we are looking at, and on the y-axis, the events or the event rate, which is recorded. So here you see the different contributions and color-coded the different backgrounds which we take into account. And all of this we denote as B0. So it has 10 background components, and we try to model them as good as we can. Maybe as a side remark now, I was mentioning the double electron analyses. So this led to this publication I'm mentioning here. Here now, this is now essentially, we take it into account in our background model for this search now, or for this analysis. So we really try to improve upon the understanding of our physics and the understanding of the detector. So this leads us now already to the possibility that we can look at some results, and results in terms of background only. So essentially what we're trying to do is we check now consistency between the background only results and the data that we are observing. So again, yes, and we do this via unbinned maximum likelihood fits. So the goal is checking consistency between data and the background model, and we do the tool is unbinned maximum likelihood fits. And what you see is that over a large fraction, the fitted model and the data agrees quite well. This is nice and good. However, and also the fitted rates are consistent with the expectation. This is also a good consistency check for us. And this leads us to say that this is the lowest background rate ever achieved in this energy range between 1 and 30 keV, which is 76 events per ton per year per keV. However, as you probably already know, when we zoom in into this very low energy region between 1 and 7 keV, where you here on the left-hand side, you see the zoom-in plot, we are observing 285 events. However, from the best fit, we expect 232 events, which is a naive 3.3 sigma Poissonian fluctuation. To address this, we do more consistency checks with our data to see if it makes sense what we are doing. So one thing which would come to mind is that if there's a problem with efficiency or reconstruction mismodeling. In order to address this, we fit to our calibration data that we have at hand with the same analysis framework to rule that out. And what we see is that we do not have an excess here, and we also observe a very good agreement between data and the model. And this essentially validates our efficiency and energy reconstruction. So a mismodeling of efficiency and reconstruction is unlikely as an explanation for our excess that we are observing. Another check that we are carrying out, or another problem which might occur, is that the shape of background that we are considering is inaccurate or wrong. And what you see here on the left-hand side is exactly this dominant LED 214 background and the Monte Carlo templates, which are more or less on the market for this. So you see three different predictions for this, and you see that the prediction that we are using actually predicts the highest rates there. We derived this spectrum especially for this work, and for this we produced the state-of-the-art spectrum together with one of our co-authors here. And the good thing about this is that it takes into account atomic effects, which are able to alter the shape of this background at low energies by a small amount. However, this is not enough to explain the excess that we are observing. So an inaccurate background is not enough or unlikely as an explanation for the excess that we are seeing. So then this leaves us with so more checks on our data are in the backup, and they are either consistent or inconclusive. And this leads us to the idea of a new background component which might be there. And the hypothesis is that maybe tritium might be in the detector. What is tritium? It undergoes beta decay. It has a low energy Q value of 18.6 keV and a long half-life. And this makes it really the perfect troublemaker for this analysis, since it will not decay away within the time that we are observing. And it is exactly in the energy range that we are looking at. It is naturally abundant and cosmogenically produced. However, on the plus side, also the xenon one-ton purification system partially removes tritium. And taking tritium into account is really unpreceded for liquid xenon TPC analyses. So the goal that we're having at the moment is testing tritium as a missing hypothesis, as a missing background, and estimate the abundance which is needed to explain the excess and see if this abundance might be present in xenon one-ton. And here you see the results. So if we include a template for tritium in the background model, this hypothesis is preferred by 3.2 sigma. We get a certain tritium rate and also a certain tritium concentration. But the take-home message here is really that this corresponds to fewer than 3 tritium atoms per kilogram of xenon. So really a tiny and minute amount, which could make up for this excess that we're observing here at this low energy region. The question is then, can the natural abundance of tritium in H2 or in water account for the observed excess? And how do we do that? First, we need to assume some tritium abundance in H2 and H2O. And the abundance that we assume is 5 to 10 times 10 to the minus 18 mole per mole. Then the number that I mentioned to you in the slide before, this 3 atoms per kilogram xenon, can be translated into a required concentration of H2 and H2O. This corresponds to 30 to 60 ppb, parts per billion. And then, given that we can operate our TPC and we're able to see light, we're able to constrain the water concentration. And this we can constrain to be at the order of parts per billion. So this is below what would be needed here. However, we should clearly state that we do not know the H2 concentration. We try to estimate the H2 concentration based on other detector performance parameters, like the electron lifetime, which we can employ to estimate the O2 equivalent concentration. And this we can fairly estimate to be also below the ppb range for the O2 equivalent concentration. However, we cannot say the H2 concentration. Is it also below ppb? We just don't know, and future will tell. So we cannot rule natural abundance of HT out to explain this excess. So what we are doing is we have tritium not included in our background model. We leave B0 unchanged since it's only a hypothesis. We cannot say it is there. We can neither say it's not there. Then we report additional significances if we include tritium in the background component. And this brings us to the part of statistical inference. And here I would like to touch briefly on what we are doing. So we already did it in the hypothesis test that I showed you before, but here I give you a little bit more flavor of what we're doing. So we're doing unbinned likelihood ratio tests, and we're profiling over nuisance parameters. And the goal is then the extraction of signal strengths of parameters of interest. And what we are testing is either the solar axion hypothesis. I will not motivate solar axions as dark matter candidates at the moment, but I will just give you the important physics properties which we are trying to constrain here, which is the ABC rate, the Primakov rate, and the iron 57 rate, where the ABC rate essentially corresponds to the coupling between the photon and between the axion and the electron, the Primakov rate, the coupling between the axion and the photon, and the iron 57 rate, the coupling between the axion and the neutron. We're doing exactly the same thing, but a little bit easier because there's only one parameter of interest for the study of neutrino magnetic moment, where we're trying to understand the solar rate enhancement, which we can translate then into a number for the neutrino magnetic moment. And to give you a flavor what the fit is able to see and constrain, I show you here now a little bit more visually the different templates which go into the fit. So in case of solar axions, there are 3 templates corresponding essentially to each of the couplings. And in the neutrino magnetic moment case, there's 1 template which corresponds to the rate enhancement. So this brings us now to results in the context of the solar axion analysis, where we do not include tritium in the background model. So what we see here is now, again, this low energy region with the data and the H0 hypothesis and the alternative hypothesis. And I tell you that the axion hypothesis is preferred over the background only hypothesis by 3.4 sigma. However, we should be fair and also address that this result is in tension with result from stellar cooling. And we should also say that when we add tritium in the background model, this significance drops quite a lot to 2 sigma. I have some more details in the backup if you're interested. This brings us to results from the neutrino magnetic moment study. So again, no tritium is in the background model. When we do exactly the same thing, but now only for the neutrino magnetic moment analyses, the significance that we are observing is 3.2 sigma. But again, it drops significantly, I think, to 0.9 sigma when we include tritium in the background component. So this gives me now the opportunity to show you a summary of the results with all significances that I showed you here today, and conclude a little bit. So essentially, we're observing an excess at low energies in this electronic recoil data. The tritium as a background component, we cannot rule it out, we cannot confirm it neither. Having said this, the solar axion model gives the best fit to data. However, it is in tension with the results from stellar cooling. And our result for the neutrino magnetic moment is the most sensitive search carried out with the dark matter detector in that field. Additional cross-checks have been done, but they are either consistent or inconclusive. this leaves the question to what next. So what next is Xenon Anton, which will give us a 3 times larger active volume and a reduced background level. And here you see what we can expect from Xenon Anton regarding the success. So with this high active volume, only after a few months of data taking, we should be able to discriminate axions from tritium based on this prediction that we are making here. And how far are we in commissioning? We expect to take data very soon. And this leaves me to thank you, and I give you here a couple of impressions from our commissioning campaign. Thank you.
Thank you, Tim. Thank you for it. It was very nice talk and also very interesting analysis. So we have our 5 minutes for questions. Any questions? You can either raise your hand or send it to me. If not, I'll start with a few questions. So at your very first plot of the data where you show the events at low energy, yeah, this one. Yeah.
You see it here as well.
Yeah.
Yeah, you see
it. Yeah, exactly. So what I'm wondering is, I imagine that your efficiency for very low energy events, like below 5 keV or even below 10 keV, your efficiency is much lower. Or so
that's
my
right.
question is, the error bars that you're showing there seem to be the same size, and I'm wondering, about the very low energies, because I imagine that it's very hard to be measured.
That is right. So what you're saying is exactly true, that for very low energy threshold, the detection efficiency drops. You can see it, for example, here. I give the numbers here. At 1 keV, it's about 10%. At 1.6 keV is about 50%. However, this is taken into account in the error bars, which are shown in the plot which I showed you above. And what you see here in this plot, or what would be the concern, is that this low efficiency is sort of an artifact and artificially enhances the event rate that you would see there, right? Because the efficiency is not correctly taken into account. This is what would be your concern.
Exactly.
So what we did is, to cross-check this, we're just removing, or we're doing a sliding window of these events. So we raise the energy threshold and see how the significance changes. And we see that the significances for the different hypotheses is really stable against raising this, against raising the threshold. So only if you're really removing all the events which are not exactly at the energy threshold, but slightly above. If you don't have any events left, of course, then you don't have any sensitivity anymore. But it's not that the excess is right at the energy threshold, and when we move it slightly, a little bit, everything is gone. It's not the case like this.
Okay. Thank you. So there is another question from one of the people in the audience asking, what do you mean by stellar cooling? Yes.
So to my understanding, the evolution of the star becomes cold, right? And we can measure the evolution, how the star becomes cold. And if we now add another mechanism that the star could be cooled by axions, so it could radiate off as well axions, then this would, if we take this into account, this would violate what we're observing from how stars becoming cold. This is my understanding of it.
Okay, thanks. We have one more question, but we won't have time for it. It's Michael, I think. So what I suggest is, if at the end of all talks we still have a few more minutes, we can come back with questions for you. Thank you once again for the very nice talk. We'll go now to the next one, which is from Nicolás Avalos, the DM-square experiment. Nicolás, yes. So, yeah, so Nicolás, are you there? You might start your video. Okay, so Nicolás will talk about DM-square, and you can go on. Thank you.
Okay, well, thank you. Well, today I'm talking about this DM-square experiment in which we are looking for dark matter daily modulation in a skip resistivity detector at the south of Argentina. So this collaboration is made up by scientists in Argentina, some of them in Brazil, and some of them in the USA. So this is a very important Latin American collaboration, and I'm very glad to present this here at this workshop. So I will talk about some introduction in which I will show what is the diurnal modulation that we are looking for in our experiment. Then I will talk a bit about the detector, which is a skip resistivity. And finally, I will talk about the experiment, the sensitivity, the setup, and I will show you some of the data that we are analyzing right now. So first, about the modulation. How do we produce this diurnal modulation? Or rather, how does dark matter is modulated? Well, we have to make a few assumptions. First, that a wind of dark matter particles is coming from the direction of CYGNOs. This is the direction in which the solar system is moving throughout the galaxy. So it is expected that a wind of dark matter that comes from the galaxy halo will come from that direction. And I think this is also important for directional dark matter searches. We also need to assume that dark matter particles will interact with the Earth core because they can lose energy or scatter. So what happens? At a certain time of the day, we have the dark matter wind that comes from 40 degrees north, and we are here in 41 degrees south in Bariloche. So at a certain time of the day, CYGNOs is just above the horizon, and we will receive this wind almost directly, and it only has to traverse the atmosphere. However, 12 hours later, the CYGNOs will be almost below us, and the dark matter wind will have to traverse almost the whole diameter of the Earth to reach us. And this produces an effect in which, well, the distance traveled by this wind, by a dark matter particle that comes from this wind, is directly related to the altitude of CYGNOs. And then if we assume that the dark matter interacts enough with the Earth and say it loses energy, then at certain point of the day, this dark matter particle will lose enough energy so that it becomes below the detection threshold. So if we have a detector that is sensitive enough to dark matter events and see some of those events while CYGNOs is above the horizon or just below, then we expect that some time later in the day, we will not see those events because CYGNOs will be below us and a lot of dark matter particles have lost energy because they interacted with Earth. I must say there could also be another effect in which not the energy but the flux is modified because of this interaction. But I am only showing here an example of what happens if this dark matter lost energy. What is important about this modulation is it's not a solar day, but it is a sidereal day. So say we are in August here, then we will have a maximum in the modulation at midnight and a minimum at midday. But 6 months later, we will have a minimum at midnight and a maximum at midday. So this is very important because the phase of the modulation, if it is correct, will tell us that what we are looking at is exactly dark matter and not another thing produced by solar day stuff. So we are very interested in looking at the modulation and seeing if the phase of the modulation is correct. Now, this modulation will be enhanced in the southern hemisphere because here CYGNOs will be only above the horizon only a couple of hours, while in the northern hemisphere, in big underground laboratories, for example, CYGNOs will be up in the sky throughout most of the day. So they will have a modulation because the dark matter particles can still scatter with Earth and so on, but this modulation will be enhanced here at the southern hemisphere. And here I'm plotting Bariloche, where we are right now, where we are taking data right now, but I'm also plotting Sierra Grande. And this is a place, which I show here in the map, which is also at 41 degrees south, but it is a place where there is an underground location which we are going to install our detector in a couple of months. I will talk about that site a few moments later. Now I will focus on the detector, which is a Skipper CCD. First, I want to list some of the particle detection experiments that use CCDs nowadays. They are, for example, DMIC and CONI. DMIC looks for dark matter, CONI looks for neutrino nucleus interaction, and they use regular scientific CCDs. Now, from Sensei on in this list, we are using Skipper CCDs, and the difference is that the Skipper CCDs has a lower energy threshold. So Sensei, DMSQUARE, DMIC-M are all using Skipper CCDs, and in the future there is a plan to use Skipper CCDs to detect neutrinos in Violeta, and also for this observatory Oscura. So first I want to talk a bit about how CCDs work, and then I will tell how Skipper CCDs are special. So I like to divide into 3 stages how the CCDs work. First, there is the charge generation stage, in which a particle interacts with the CCD. This is a silicon bulk, and in the front and back end, we have electrodes that produce an electric field in the silicon bulk. So whenever a particle interacts with the silicon bulk, it generates electron-hole pairs, and because of these electric fields, the holes drift towards the front end. Here in the front end, we have a pixel collection well where the charges are stored until we choose to read them. Then this readout is produced by moving the charge. We have a mechanism that allows us to move the charge from one pixel to the next, first vertically, as depicted here, and then horizontally toward the sensing node. In the sensing node, what we do is measure the voltage. It works like a capacitor, so if we know the capacitance and the voltage, we can calculate the charge, and we can know how much charge was collected in each of the pixels. Then we can amplify this and obtain the signal. And finally, what we do is reconstruct the image and analyze it. So this is an example of an image obtained by a regular CCD, in which we can see muons and electrons, also alpha particles, and what is of importance for us in this experiment are these diffusion limited or point-like events, because we expect that the dark matter interacting with the silicon will only produce 1 or at most 2 electrons of excitation in our silicon. But here I'm focusing on the charge readout stage, because this is what makes the Skipper CCDs so special. So in a regular CCD, we have this method for reading the charge, which is called correlated double sampling. What we do here is, during a certain integration time, we measure the sensing node without the charge deposited in it. So we have like a 0 level signal. Then we move the charge towards the sensing node, and we obtain the value of the signal of the actual charge that was deposited in the pixel. So the difference between these 2 stages will be the voltage difference due to the deposited charge. Now, this is a very good method to get rid of the high frequency noise, but we are still sensitive to the low frequency noise. And if we plot the noise versus the integration time, we will see that there is an optimal time. We are taking into account both the white noise and the flicker noise. So there is an optimal integration time beyond which we cannot further enhance the noise. We cannot make the noise smaller by increasing the integration time, because then the low frequency noise will make us that we have more noise. So the regular CCDs are dominated by this low frequency noise, and this sets lowest noise at around 1.8 electrons. It could be lower, but there is a lowest possible noise. Now, what happens with the Skipper CCDs? The only difference between a Skipper and a regular CCD is the readout stage. So now with the skipper CCD, we can read the same pixel, the same charge of the pixel several times, and we are not destroying it. It is not affected in any way. So this means that we can read, say, 1,000 times the same charge, make the final average, a final value of the pixel as the average of the samples, but then reduce the statistical noise by the square root of the times that we read. So in this way, we are getting rid not only of the high frequency noise, but also of the low frequency noise. And here we see an example of an image that is only made up of noise, where we see a histogram at the 0 electron distribution, which has a certain width, say 3.5 electrons. But with the skipper CCD, we will assure that all of the pixels in the background here in green have 0 electrons, and there is a single pixel with 1 electron depicted in orange here. And when we take a look at the histogram, we see that there is a very sharp peak in 0, 1, 2 electrons. So we will know exactly which pixel has 0 electron, which has 1, and so on. So then we can reduce the energy threshold from the 50 electron volts of the regular CCD to the silicon band gap, which is only 1.1 electron volts. So now I will talk about the experiment itself. What do we expect to see? Well, we are looking for low mass WIMP interactions. Because of the low detection threshold of the skipper CCDs, we can search for dark matter interaction with electrons. This is what the Sensei collaboration does, and they use the same detector than us. For Proto Sensei, now they have a better skipper CCD for actual Sensei. Now, the sensitivity of our experiment is enhanced for WIMPs of mass of order the Melo. So we're looking for low mass. Now, we are running the experiment on surface. This allows us to explore a section of the parameter space where WIMPs, for example, will scatter before reaching detectors that are buried deep underground. But this is not a zero background experiment. We cannot model the background for our CCD. So we cannot improve our sensitivity right now by adding more detection mass. Because if we cannot separate the noise from the background and we see nothing, then we will see the same if we add more detectors. So our only option here is to look for a signal modulation. And therefore, if we see a modulation, we can say, okay, the events that produce the modulation are because of the dark matter, and the rest of the events are background. This is our way of separating the background, the modulation. I'll show you the experimental setup now. This is our detector. You can see it's very, very small. It's a rectangle of 1 × 2 centimeters of silicon. It is 200 micrometers thick, and we have almost 1 million pixels here. And if you take a look at the mass, you will see that it is only a fraction of grams. It is less than 100 milligrams. So it is a very, very small detector. This detector is divided into 4 channels, which we can read simultaneously, and is packaged inside a copper housing, which we have inside a vacuum chamber. Why do we need this vacuum chamber? Well, we need that the CCD is at less than 114 degrees Kelvin, so that we reduce the thermal noise that produces dark current events. But at that temperature, if we had the CCD in contact with the air would condensate and damage the detector. So this is what we have the vacuum chamber for. And how do we lower the temperature of the skipper CCD? Well, we have a liquid nitrogen tank. This liquid nitrogen is filled, and there is a thermal coupling called what we call cold finger. It is a copper cylinder, which lowest end is in direct contact with the liquid nitrogen, and its highest end is in direct contact with the skipper CCD. So in this way, we can have our skipper CCD with a temperature of about 115, 120 Kelvin, which is perfect for what we need. We also have a resistor to measure the temperature and see that we are doing the things right, and we are. let me show you some data. This is an example of the image that we collect with our CCD. This image was taken with 1,000 samples per pixel and with a hardware binning of 1 × 5. This means that 5 consecutive rows of the actual CCD are compressed into only 1 row of this image. And this is done via hardware, it's not software. I mean, we are reading 5 rows at the same time. And why do we do this? Because we need to search for a diurnal modulation. So we cannot have the CCD exposed for a very long amount of time, because then we will not be able to separate when each event happened. So in this way, we can be assured that the CCD is not exposed more than 1 hour and 15. And in fact, all the CCD is exposed during that time, at the same time that we are reading it. So there is also some pre-processing that we do to obtain this image. First of all, we have to average the value of the pixels. Then we subtracted the median of the overscan. The overscan is a region of pixels which were not exposed during the same time as the rest. So they set a distribution for the value of 0. We know that they have 0 charge. So when we subtract the median, we will know that all the rows have been normalized correctly. And we have also calibrated the image in electrons. When you look at the histogram of this image, you will see that there are separate peaks for 0, 1, 2, and so on electrons. And you will also notice that these peaks are not as sharp as the ones I showed you before. This is because in order to have sharper peaks, we would need more samples per pixel. But if we had more samples per pixel, then we would need to increase the exposure time because we would need more time to read our detector. However, we can exactly know how many pixels in our image have 0, 1, 2 electrons by integrating these peaks. We can make a Gaussian fit, and we will know exactly how many electrons are there in our image. And specifically, the distribution of 1 and 2 electrons are the ones that will matter to us. We will look at those counts, and we will search for the modulation of those counts. So there is further analysis ongoing. We are working on an algorithm to subtract the correlated noise, which allows us to make the peaks sharper without increasing the exposure time. We're also analyzing events that weren't produced by dark matter, for example, muons, electrons, X-rays. We can extract these events and we can count the charge and know how much energy they have. But most important, we are understanding the response of the CCD. What happens when a pixel saturates? What happens when an event is produced in the horizontal register? What are the problems with charge transfer efficiency? So this is very important in order to provide expertise.
What do you mean by stellar cooling?
Just continue.
Okay. So,
okay. Add another channel how planets can cool. This would violate.
Sorry, someone must have a microphone open. I cannot see who that person is. I'm trying to shut your microphone, but if you know you're talking about stellar cooling, could you please, you know that you are, and can you please shut your microphone down? Thank you very much.
Okay. So what is important is that we are understanding how the skipper CCDs work, and we will have more expertise for the next generation of experiments. And right now we are taking data at surface level in Bariloche, but in the future we are planning to move the experiment to an underground location in Sierra Grande. And in this location, which I show you here, we expect to have
excuse
less.
Me, you will have 2 minutes plus 5 for questions.
Yeah, I'm finishing. Yes. So at this site, which is around 400 meters deep, we will from coast race, and this was already used in the 90s to look for dark matter and strange interactions in the 90s using germanium detector. So it is a place that we are very excited to go and take measurements. So to sum up, with our experiments, we are looking for diurnal modulation of low energy events using a simple CD detector. This modulation will provide a unique signature for the matter. And we're also studying the properties of the skipper CCDs. These properties will be very useful for the future experiments. And as an outlook for our research, we're looking forward to have preliminary results by February 2021, hopefully, because that's when I must present my thesis. And we will make a shallow underground run from March next year at Sierra Gran. So thank you very much for your attention, and you can make questions now.
Thank you. So we have time for one question. So here's a question. What is the number of events of dark matter particle collisions per day to be expected given the amount of dark matter present in the Milky Way on your detector?
Well, we haven't, we don't know exactly. We cannot predict the interaction because in order to do that, we would need to know how the interaction happens. We would need to understand what are the interactions with our detector and with the Earth. So we do not have yet an exact number for that. We expect at least that we can see, and I mean, in order to our experiment to work, we would need that at some point of the day, there is at least one event, and at certain point of the day would be at least 0 events. So then we would see the modulation. But right now, that is not an answer, a question that has an answer.
But you know the number of events per given cross-section. So if I give you a cross-section of 10 to the minus 43 square centimeters, you can compute it, right? So
sorry, I couldn't catch that.
I guess probably the question was about, for a given benchmark cross-section, what's... Yeah. So if I give you a cross-section 10 to the minus 44 centimeters square or minus 45, I guess you know the number, right?
Yes, we have some examples here. If you take a look at this line, for example, we assume a WIMP of 10 MeV and a cross-section of 10 to the minus 37 centimeters square. Then there is a preliminary calculation of events per kilogram per year. And this is versus the detection angle. So this is correlated to the altitude of signals. And then these are the expected events that we have per year. Now, with these numbers and with our detector, we would see nothing. So we are still working on what we can actually see with our detector. Ignore this dashed line, it's wrong.
Okay, so unfortunately, we don't have time for other questions. So it seems that we will be on time. So I'm asking, there were 2 more questions here. So I'll ask that you send it directly to Nicolás. And I'm sorry, but we really don't have time. So we'll move now to Elisabetta. Baracchini, I hope I said it right, and she'll talk about direction dark matter searches with CYGNO INITIUM project. So Elisabetta, if you could.
Okay, can you see the slides?
Yes, now we can.
Thank you much, and thank you for giving me the chance to present to you directional dark matter searches with the set the context. We already, yeah.
No, the sound was bad, but now it came back in. So.
Oh, okay, sorry.
May I suggest?
So I can stop. I can stop my camera. So
For
maybe.
the beginning, yes. So we minimize.
Yes. Thank you. Okay, sorry for the so about dark matter searches, the main region where we are looking now for dark matter is, okay, we have the claim by Dama that it sets more or less in this region of the parameter of dark matter masses versus cross-section. Then we have typically solid state experiments, also like DAMIC, the one that's been discussed before, that go in the, let's say, trying to explore lower mass regions for the masses. And then we have approaches which are mainly in liquid noble gases, and we heard the talk this morning. We will have other two talks about this kind of approaches that try to explore, let's say, going below, meaning in the explore more in the terms of cross section. So we like to think about our approach on directionality as a third way in which you like to explore, let's say, diagonally, because this is the only approach that can really allows you to break the neutrino floor for both the spin independent and spin independent interaction. So the reason why we want to use the directionality is that you can think of us pictorially as we are driving to Cygnus, having this dark matter wind blowing in our hair, and also as Nicolás explained before me, this introduces modulation, several modulation, and you can use this modulation to have a positive and an ambiguous identification of dark matter. So the point is that typical experiment, what they measure is the energy of the recoil. So this energy does not possess a peculiar dependence or a peculiar feature. It's just a falling exponential, which also, unfortunately, as a shape, looks like the background. So here we are not like, I don't know, LHC, where you have a peak of the X on top of a background. Here you have a falling exponential on top of a falling exponential. You can exploit the annual modulation that is given by the fact that our Earth rotates around the Sun. So half of the year you are going in the same direction of the Sun, and the other half in the opposite direction. And this introduces an annual modulation. That is what the Dama collaboration measured. The problem of this is that it's just a few percent, because this is given by the ratio of the Earth velocity with respect to the Sun. So this will give you just a couple of percent, and you need therefore a larger stable detector to be able to see this. On the other hand, the directional dependence, given the fact that every second, every moment of the day, Cygnus will be in a different position in the sky, will give you another one effect if you plot this in galactic coordinate that is shown here. And this is another one effect that no background whatsoever can mimic, and therefore this can be used as a positive tool for a positive identification of a dark matter signal. Directionality helps you also for other reason. It allows you to also improve the background rejection because you are able to reject isotropy, and background is going to be distributed isotropically in galactic coordinate, no matter what how your detector is composed, because galactic coordinate rotates. On the even more interesting, this allows you to leap beyond the neutrino floor, and this means that not only that you can continue dark matter searches beyond the neutrino floor, but you can actually do neutrino physics with both nuclear and electron recoil, because the directionality allows you to discriminate also the electron recoil coming from solar neutrinos. And the third thing, even more important, that once dark matter will be hopefully discovered, directionality allows you to probe dark matter nature, also in terms of dark matter astronomy, so the capability of measure the halo properties and so on. That's why we think it's an extremely important path to follow. So the most natural architecture, if you want, for experimental approach to directionality is a time projection chamber, a gaseous time projection chamber, because this is inherently a three-dimensional detector that is sensitive to both track sense and direction. And let's say the game to play here, what we need to optimize and develop, is the best choice for signal amplification and readout that allows you to have the full capability to reconstruct the topology of the different track for both directionality and also background rejection, because here below you see nuclear recoil on the left and electron on the right with before and after the drift, and now they look different, so you can exploit the shape of the track to do background discrimination. And you want to do this with enough granularity to see very nice direction, but at the same time you want to have also an approach that can be scaled up to very large detector, because given that this is a gaseous detector, typical density that you can reach are of the order of, let's say, typical weight is 1 kilo per cubic meter of detector. And so, of course, the drawback of this approach is that you have a low mass, a low exposure in this game. So you need to have a big detector. An interesting approach, so one of the problem of time projection chamber with large volume is the diffusion. Of course, diffusion can spoil both the track properties in terms of pattern, meaning the difference between a nuclear and electron recoil, and it can even spoil even more the direction. So there has been a very interesting, let's say, development in the past year. Actually, this started in 2000, and is the operation of time projection chamber with negative ion drift gases. So this happens when you add very electronegative dopant to the gas mixture. Even a couple of percent is enough to induce this kind of operation. And what happens is that the primary ionization are captured by these electronegative molecules at very short distance, less than 100 microns. Then this becomes negative ions, and are the negative ions that drift to the cathode, and then at the anode, and at the anode the electron is stripped, and then a normal avalanche starts. The advantage of doing this is that negative ions have similar masses than the gas they're traveling through, so they can exchange energy much more efficiently, therefore reducing the diffusion down to the thermal limit. So with this, this allows to build a big time projection chamber, which still can be highly sensitive to the direction and high granularity. A second issue of this kind of approach of time projection chamber is that you don't have the T0, the start time of the event, like you have, for example, at accelerator or in other application of time projection chamber. So this means that in principle you cannot, let's say, define the position of the track along the drift direction. Negative ion drift gives you another advantage also in this sense, that is that actually multiple ions are created with this game with different masses. And given different masses, if they start at the same point, but they travel at different masses, so with different drift velocity, these two different charge carriers will arrive at a different time. And this allows you to effectively fiducialize also along the drift direction. This is something that is a technique very commonly. So this has been the drift from CS2 and CS2 and O2, and also with SF6 more recently. So setting into this context, there is the CYGNO and INITIUM project. So our approach and our goal is to use a 3D optical readout with CMOS and PMT as detector. So how it works? We use a triple gem as amplification stage. During the amplification stage, not only charge is produced, but if you also light. And in particular, we are using helium CF4. So our light is circulating in the visible. So at the end of the amplification process, rather than collecting this information, if you want, through that measurement of the charge, we actually measure the light. And we do it in two ways. We measure the light with a PMT. The PMT will give us the inclination of the track with respect of the drift direction, as is depicted and is clearly here on the left. Then we also measure the same light with a CMOS camera that gives us a very, very nice picture of these tracks. This camera, in particular, this scientific CMOS, has lower noise than CCD. This kind of technology is pulled by the market, so you see very big development very, very quickly. And with a proper optics, because we have a lens in front of this camera, you can image a large enough area as much as you want. And I will show you that we are actually doing this. There is not a talk by Florian on West. So the combination of these two information allows us to build a prediction track. So this is the general concept. We started working with helium CF4 at 1 atmosphere, and what happened was that I got this ERC grant in order to apply the same technique with the negative ion drift concept, and therefore the idea is to add the SF6 to induce negative ion drift, and this is called INITIUM, and that's why you also see CYGNO and INITIUM usually together. So next slide. So here are the picture of the tracks. I have to tell you guys that whenever we take data in the lab, it's really, to me, it's really amazing every time to see the tracks by side. And I would like to stress that these are raw data. So these are the raw images that we get of this data. You saw also in the previous talk also how the CCD can produce these nice images. These tracks looks much bigger than in the CCD, just because I would like to remind you that we are looking at this. Actually, we are looking at the amplification of the track, and we are looking at this with an optics, so with a lens that enlarges the effective area of our sensor. And let's see how much. So yeah, what you are seeing here. Okay, sorry. So this is a timeline of our development, and what I will be showing you now is the results from 2017 on. So as you see, we are going through two different, let's say, two parallel line, which is on the top electron drift and on the bottom negative ion drift, because we are developing this project together towards a full experiment between 30 and 100 cubic meter. So this is the picture of Lemon. Lemon is our medium-sized, let's say, prototype. So in this configuration, we have a 7-liter active volume and the 20 centimeter drift and a 20 by 24 centimeter square readout area. So in this configuration, with a proper distance of the camera and a proper lens, we look with one single camera at this 7-liter volume. So the area imaged by the camera is 20 by 24 centimeter. And here you see also how the spectrum of helium CF4 nicely match, at least in the visible part, nicely match the spectral response of the CMOS, which is up to 70%. It's actually higher because these are all the models of the camera that we are using now, an even improved one. Here are some results by Lemon. So first, for example, the response to X-rays, and this allows us also to understand which is our energy threshold. So this is how iron 55 looks in our detector, like a round spot, because mainly of diffusion. And this is how the iron peak looks like in the data. So from this, and also let me stress again that this is with an old camera that is not as sensitive as the one that we are using in this right moment. With this old camera, we were collecting about 500 photons per keV, and comparing this with the noise that we measure on the sensor, for example, in this configuration, we could our effective energy threshold is 1 keV in order to not have, let's say, fake clusters created by the sensor noise. And at this energy, we measure 15% energy resolution, which is consistent. It's good for a gas detector. It's consistent with what you expect at this energy for a gas detector. Another interesting study that we did was with, these are long tracks, and these are high energy electrons. And the goal of this study was to demonstrate, as we actually did, that thanks to the high granularity of our readout, we can exploit the diffusion and fit for the diffusion of our track, and in this way measure the absolute Z coordinate, which I told you is one of the issues of this application of time projection chamber in dark matter, because of the fact that you miss the T0. So here it's depicted pictorially. Here you see these two tracks on the top. You see the tracks are very clean and crispy, I would say, when they are close to the gem, because they are not diffused into the gas, while when they are far from the gem, they are let's say more smooth. Okay, so you can fit for this, and you actually can infer the Z coordinate, so the coordinate along the drift direction, about with 15% resolution from both the PMT and camera. So this is not perfect, but it's still better than nothing. And let me remind you that this is done without the use of negative ion. All the data that I'm presenting for the moment is with combat, and we will start the test with negative ions at the beginning 2021. This other measurement is extremely interesting, for maybe one of the most interesting, and it's a study to determine our efficiency on low energy nuclear recoil and our capability of discriminating them from electron recoil. In this particular analysis, the electron recoil we had, where we only had iron 55, so we don't have a spectra of electron recoil. With different energy, we have a fixed energy. This is just because we didn't have availability of another source at the moment. After this, we took data with cobalt, so we will produce a new analysis with this. So anyway, this allowed us also to further develop our reconstruction code, of which here I give you like a screenshot. So our code works with the DBScan procedure. It does multiple iteration to find the different track pattern, where pattern I mean different specific ionization deposit. So very large and constant for nuclear recoil like this, or fainter and clusterized, let's say, for electron recoil. Then it uses a morphological geodesic active contour to connect this spot, and you can see here how with this we can reconstruct very different shapes. Here you have a picture of a 5.2 keV nuclear recoil candidate, which also seems to show some direction and sense, but we are still developing our directionality analysis. And here on these slides, the results of this paper. At the moment, we are using only a single variable to discriminate these two different quantities. So the analysis is not optimized, it's very preliminary. It's just to give you a feeling of what we can do. And using a variable on this variable on one value, we can obtain nuclear recoil efficiency for energy below 20 keV with a 99% reduction of the iron 55. So we are very happy about this. We're very happy about this because we believe that employing more variable and possibly multivariate analysis and even machine learning, we can significantly improve over. Currently, we have two new prototypes, one very big and one small one. I'm showing you the very big one. The very big one is called Lime. This is a 50-liter volume detector, and the 50 liter is made by 33 by 33 centimeters square without area. So here, one single camera, which is about 50 centimeters far away, with the proper optics, is looking at 33 by 33 times 50 centimeter drift. Here are the picture of Lime with its cage and our technician in the lab. We are already starting operating it. We have preliminary measurement. We confirmed our 15% energy resolution on the iron 55 along the full camera, so even for 50 centimeter distance. And here we are employing this new camera that I'm telling you, this Orca Fusion, which has a larger sensitivity, in this configuration, and even a lower sensor noise. So we hope that we can do very nice measurement. We took data with americium, beryllium, and cobalt, so nuclear recoil and electron recoil sample, and we are analyzing that. And we hope we will have soon new results, and we can publish a paper. The plan for Lime is to bring it underground Gran Sasso at the beginning of 2021. So this is the picture of this barrack that was identified. It's here in between two holes. It's the connecting tunnel. And here are the engineering design of how we plan to work with Lime. And so there is also, as you can see, there is also a space for a 50 centimeter water shielding plus 10 centimeter copper shielding. So this was, the preparation of this was slowed by COVID, as you can expect, as you can imagine, but the completion of this area is expected for, let's say, the first semester of 2021. So this means that we hope that we can bring Lime underground before the summer. And we already tested that the stability and
Elisabetta, I'm sorry, but you have 5 minutes plus 5 for questions.
Thank you very much. I think I am inside the time. So we tested the stability of Lime also because, of course, if we want to put it underground, we need to be sure that the detector is properly working and stable. And we verified, so we set up a very simple procedure of auto recovery of if in case of jam hotspots and also trips, which is also discussed here in this paper. And we observed with this simple procedure, we observed on Lime a good stability, meaning less than one, let's say, sparking or something like this per hour. That is in agreement with the fact that, of course, Lime has larger jam than lemon. So we're very happy about this. Plans for the future, all of this that we are doing is to finally build up a 1 cubic meter demonstrator that will be CYGNO and INITIUM, because it's the same detector, just operated with slightly different, let's say, setting or operating condition. and this is a schematic of the 1 cubic meter. So the idea is actually that the 1 cubic meter will be composed of 9 lime equivalent, let's say, detector for each side of the 1 square meter, because this will be there will be a central cathode, that is this one, and 2 50 centimeter back-to-back TPC with 9, let's say, module like lines like this, looking each one at 33 by 33 square centimeters. So that's why it's very important for us, this lime detector, because with this underground we will measure effectively the same performance that we expect for the 1 cubic meter, that will have about 1.5 kilo of mass, and that the very good news is that this is already funded, which is something that it's not trivial, let's say. Okay, and we started, of course, working and worrying more than working on the background that expected. So this is a simulation done with Jean-Fort of the expected preliminary background, and our very ambitious goal, we understand that, is to try to get to 10 to the 4 gamma per year between 0 and 20 keV in the interactive volume. This because we, let's say, expect also from other studies, from for other collaborators in the field, that you can reach about 10 to the 5 discriminating power around 10 keV. So we envisage an external shielding of 200 centimeters of water plus 5 of copper in order to kill all the background coming from the cavern. But we see that even with this, we have a very big contribution of background coming from the gems and the CMOS, as one would imagine. The CMOS especially than the gem, because this object has never been really used for for relevant searches. So this object is extremely radioactive. So we started a campaign to measure the activity. Here you see all the different camera of which we measure both the radioactivity or the sensitivity, or the camera that we are let's say taking into account to try to find the best one. And also recently what we did, because when you measure this camera, you measure the full body, so you cannot really identify what is the bad guy, let's say. So what we did is a camera autopsy, in the sense that we dismounted the camera. Here you see a picture of the pieces, and these pieces to be measured. So we hope that we can pin down which is the main components that are giving us radioactivity, and substitute them with not radioactive material. So actually CYGNO and INITIUM sets into a wider context of directional dark matter searches, which is called the CYGNO's, let's say, proto collaboration, where the goal, you see that these are, let's say, the site, or better the collaboration, the groups that are within this proto collaboration, so Australia, Japan, UK, and US, because the goal of this proto collaboration is to eventually develop and build a multi-site, multi-target galactic recoil observatory at the ton scale that can probe dark matter below the neutrino floor and measure solar neutrino with directionality. The common point, we are still developing this, we are still working on the best choices of amplification and readout, and also gases, but the main point is that we will use helium and fluorine to be sensitive to order GeV whip masses for both spin independent and spin dependent. We want to reduce diffusion, so either with negative ion drift or cold gases like CF4, because the gases that we use is actually at a good low diffusion. Of course, three-dimensional fiduciarization and directionality and energy threshold of the order of keV. And this is a picture of the last proto collaboration meeting. So here are just plots of this very long and informative paper that we recently put on archive, where you can find a lot of information about this project. And these are the sensitivity that are expected for CYGNOs, that is 1000 cubic meter and 6 years, with different, so this is, let's say, the best and worst case scenario in terms of capability of electron rejection. What we also verified with this paper is that we really need to test and demonstrate on a order cubic meter detector the actual rejection performances and directional performances in order to be able to let's say to make a real prediction of our sensitivity, because of course the sensitivity is highly dependent on this. The good news is that already a 10 cubic meter detector can pose extremely significant constraint in the spin dependent, breaching the xenon neutrino floor in the spin dependent coupling. And then for the spin independent, a full detector of 1000 cubic meter will measure and identify between 10 and 50 neutrino event with coherent from coherent scattering. And so I will conclude to tell you to stay tuned for a flock of genius birth, since I'm just one of these, and there are other these other projects. And thank you very much for giving me the chance to present this project to you. Thank you.
Thank you, Elisabetta. Very interesting. Unfortunately, we do not have time for questions. Tim Wolf has a question. Tim, I would ask you to send your question directly to Elisabetta in the chat. And so we'll move on now with Greg Rischbieter. I'm not sorry if I didn't say your name correctly.
It's close enough, but thank you. Rischbieter.
Okay, and he'll tell us about looks. So Elisabetta, if you could unshare your screen, and then he can load his, okay, thank you.
Yeah, perfect. All right, thank you, everyone. I will be presenting an overview of the LUX dark matter direct detection experiment, as well as highlighting a few things that we've done in the last year and a half and things to look forward in the upcoming year, as we're expecting these multi-ton scale direct detection experiments to come online in 2021. Just quick outline, going over the LUX basics, because we've had a few dark matter talks, or TPCs, Xenon TPC talks already, so I can kind of whiz through this. But go through really the meat of LUX during 2013 to 2016 while we're taking data. I'll spend a bulk of this talk going over the post-WIMP search analyses, specifically these new techniques that we've been fleshing out, understanding our detector better, getting new physics out of it, and developing new techniques that will really, these next generations of multi-ton Xenon TPCs and what we can do to expand our search region. And then I'll end the talk with one of the bigger projects that we've been working on for a while that should be finished soon and out in 2021 before these new experiments come online, which will be the effective field theory analysis with a full exposure. So, we are an international collaboration, forming all the way back in 2006. However, the last time we met with decent numbers was 2018. With LZ coming online next year, a lot of us have been dropping off, but with the pandemic, this will probably be the last time that LUX has met in person solely for LUX reasons. But it's been a strong effort for over a decade from dozens of institutions all over the world. So LUX itself was a dual phase xenon liquid and gaseous TPC that was held almost 5,000 feet below the Earth's surface at the Sanford Underground Research Facility in Leeds, South Dakota. So showing the beautiful above ground surface level versus the very intriguing underground lab in the Davis campus, same place where Ray Davis conducted his neutrino searches that won him the Nobel Prize. So at a quarter-ton active mass, and its tenure lasted about 4 years here in the Davis water tank. So just an overview of the timeline of LUX's stay during that its main science runs. So although the collaboration was formed all the way back in 2006, LUX didn't actually begin moving underground until 2012. So a good 6 years of planning and above surface assembly, and calibration runs, commissioning runs, and just science before it can be put together and taken underground. So about a year later, we had the first science run begin in April with our very first recorded WIMP search event on April 23rd. And then with a 95 live day search for the WIMP search 2013, and we reported those results in November. Then shortly after detector upgrades, we began our longer science run over 300 live days over the span of close to 2 years. However, after LUX was done taking WIMP search data, we were able to do some last-minute calibrations, which really aided understanding how xenon detectors work at different energies, that we were able to do a lot of good physics with in the following years, until the final decommissioning in 2016, when after LUX's decommissioning began, we released the first, the full 430 live day results. And LUX was eventually, now remains in the lead visitor center in South Dakota, where you can go see it, read all about it, as well as all the other science that's going on at the Sanford Underground Research Facility. And I'll just highlight that I didn't enjoy the collaboration until right before this, so I did miss most of the party. However, it does highlight that there's been no shortage of science to do, despite LUX no longer taking data. I can go through this pretty quickly. We had a good overview of signal production from our first talk for Xenon 1 ton. So I'll go through this quickly. Particle comes in, you have prompt scintillation light detected almost immediately, giving you your S1 signal. You can drift electrons out if they're between the grids, which we call the forward field region or the drift region. Those electrons are then converted into a light signal in the extraction region. And so you get 2 light signals, your S1 and S2. You get full 3D reconstruction based on the S2 hit pattern, giving you the XY position, and the time between these 2 light signals give you the drift time. And we're able to, even more so, we can take the size of each one of these signals and if we know what our detector gains are, your light collection efficiency and the conversion from electrons to light and that detection efficiency, you get back the original quanta produced from that interaction, and you can actually then construct what the energy was, depending if you have an electronic recoil or a nuclear recoil. And as you can see in this moving graphic, based on what the interaction type was, the flow of energy through these different channels to produce S1s and S2s vary. So to probe this, and before you start taking science data, you will need to understand how your detector behaves to ER and NR interactions. So the 3 main calibrations that were done throughout LUX's 4-year tenure in the Davis campus were ER calibrations using tritiated methane, so continuous beta decay out to 18.6 keV. This was injected directly into the xenon that removed via purification, so you're able to get a uniformly distributed ER calibration. We also were able to do nuclear recoil calibrations using a DD neutron generator. So this was an external beam pointed directly at the TPC, and ended up with leading to measurements between 0.7 to 74 keV nuclear recoils. We did have earlier californium and americium beryllium calibrations before Science Run, the WIMP Search 2013. And this was a major improvement, allowing for a more saturated or a more robust nuclear recoil band. And our third main calibration source for Krypton 83M injections. This is decays in 2 steps, a 32.1 and 9.4 keV emission, but these are only nanoseconds apart, so you effectively have a 41.5 keV source. So this was outside of our standard WIMP search, so we could do this throughout all the science runs, and it's useful for measuring those gain factors for your S1s and S2s. And once you have calibrations underway, you can start taking data. So LUX's first science run reported in November of 2013 was the world's first sub-zeptobarn dark matter detector. At the time, world-leading results for this data for spin-independent WIMPs and your spin-dependent interactions with neutrons. And so I'll note here that this was a near uniform drift field, about 200 volts per centimeter. A very well-behaved detector, a nice data set to work with. On LUX's second science run for 2014 to 2016, things weren't quite as nice. We had a nice 332-day live days taken. However, our detector gains were varying with time. Those introduced an extra challenge. The bigger challenge was that we had a non-uniform drift field. And so you can see here we have the.
Greg, sorry, but you have 3 minutes plus 5.
Okay, thank you. I will speed up then. And so this was, we had different drift fields, and this allowed for, it was a challenge to model the detector with this varying drift field. However, we were able to do a lot of good physics by probing these different detector conditions. And so again, combined with WIMP-Search 2013, we were able to set world-leading limits, although these were later improved by newer searches such as Xenon 110, as you heard about at the beginning of the session. After the science run, we were able to do extra calibrations. Most importantly, the carbon-14, which has a 156 kV endpoint. So this allowed us to probe our detector out at very, very high energies, which is necessary for, such as a effective field theory search where you want to go out to higher energies. We heard about modulation searches and diurnal searches. Lux was able, due to its long, just after the WIMP search analyses, able to set constraints on modulation for both annual and diurnal. Dama Libre is the only positive claim of a dark matter direct detection, and we're in strong tension with those results. We don't show any significant modulation for either the annual or the diurnal. I mentioned that our detector had a varying drift field, and so while this was a challenge to work with, we were able to really probe the physics of signal production in xenon at different fields, such as discrimination between ER and NRs, how much ER leaks into your NR band, as well as start looking at the pulse shape discrimination between these two interaction types by the shape of the S1s. And you can actually see that there is an offset between ERs and NRs, and by introducing this, you actually improve leakage substantially the most at your lowest fields. I'll quickly highlight these three analyses that we're doing the similar phase space of WIMP detection, using the ER channel to detect nuclear recoils such as Bremsstrahlung and the Migdal effect, where you essentially have a produced ER for your nuclear recoil. And this allows just an increased signal size for these low energy nuclear recoils. So while these aren't world leading limits, especially for the heavy scalar mediator, it is a way to take this xenon technology and extend it to lower masses. You can do something similar with a single photon study where xenon scintillation light ends up actually producing about 20% of the time an additional photon on your PMT. And so by looking at the rate of this double photon emission, you can rule out xenon scintillation light from dark counts. And so you can actually get true single photon S1s, extending your search region even further. And then taking it one step further, you can completely omit the S1 and do an S2 only analysis where you look only at the ionization channel. This is a bit tricky because you don't get the drift information without the S1, but you can extrapolate it. In this case, we use machine learning techniques to look at the pulse shape of the S2, and again, extending your search region. And the reason for showing these three, these are not world-leading limits anymore because of improvements by larger detectors. However, as we're waiting for LZ and Xenon N-ton to come up, and we start expanding our search region, we now have three unique ways to probe this region of phase space that introduce different systematics, and so it's a good way to verify and check results. I'm running out of time. I will quickly summarize.
Sorry, Greg, I messed up. You still have 5 minutes to go plus 5.
Oh, beautiful. Okay, thank you. All right, so I can pace myself a little bit through this last portion of the talk because I would like to introduce people to the effective field theory analysis. So this is reaching out to a new region of interest of your data by going out to higher energies. And so we do have good motivation for interactions between your basic spin independent and spin dependent WIMPs. And so essentially it allows for inclusion of momentum and velocity dependent terms to your Lagrangian. And so you can end up taking all these different interaction terms all these different operators, and try to constrain what those coupling constants are. And so you can just zoom in on the difference between your standard spin independent versus the EFT equivalent of that, and you do have an order of magnitude increase at 100 keV nuclear recoils. So because now that you have more of a significant rate at higher energies, you want to extend your region of interest to higher energies as well. So this was first tried with Lux's first science run, where you can see the WIMSearch 2013 data up here in the upper right. And we have the background model down here in the bottom left. And you can see there's a clear departure from our expectations with events below the background or below the NR band, some falling into the NR band. You do have this krypton 83 injection, but that's been cut out due to as a region of interest because we don't want this low leakage contaminating the NR band. Because of these mismodeled backgrounds, you can't use anything fancy like a PLR. But there are ways to set limits with this. However, the takeaway here is that when you extend your WIMSearch region to higher energies, you do need more robust background modeling. And so that's the goal of what Lux have been doing recently, of taking the rest of the Lux data and improving our background models, creating more background models so that we can use a PLR for a full exposure EFT analysis. So instead of using the Geant4 based model that I showed back here, we want to use something more robust, more efficient. And so that we've been using the Noble Element Simulation Technique, or NEST, to build a detector model that not only reproduces all Lux data, but then you can also use NEST's what already exists within the NEST software to extrapolate beyond what's in our data. So we were able to, NEST is an open source third-party software that already does an accurate modeling of xenon microphysics, but it's based on world data and averages out existing data sets. So instead, we tuned it to solely reproduce Lux results, and we do have good agreement for those different field bins through different throughout the time-dependent structure of that WIMSearch 2014-2016. And once you have your xenon response model, you can begin fitting to your background. So specifically, we blinded off the region below about 80 keV electronic recoils, which is the EFT search region, about 300 PhD S1s, and able to fit to those monoenergetic peaks, including multiple scatters. And we already have good activity rates for all these different detector components coming from our assays, but we're able to fit within those errors to get a good background model. I'll conclude talking about one of the harder backgrounds to model, because as we saw, there are different backgrounds besides just your ERs that you need to take into account. One of them are these, what we call gamma X events, where you have a multiple scatter, but you only see one detected S2. This is because you have regions of your detector that do not produce an ionization signal. So we can end up looking at these actually, or extrapolate to these by looking at what we call near miss events, where they're double scatters that are near these S2 less regions. So by taking a population of these near miss results, you can make sure that you're able to model correctly the light and charge collection, as well as the light behavior in your PMT arrays, such as which PMT gets the most light versus the top-bottom ratio between your two arrays, and the size of your S1 hit pattern in the bottom PMT. And so this essentially allows us to try to use this extra information to create a gamma X model, extrapolate these near misses at high stats using NEST again, to create a robust PDF that you can use in a PLR for these events. And by being able to reproduce the light collection, you can then start looking at actual data and try to compare these events much better to the data that you have. And so I'll just conclude and say, with this and the additional modeling techniques, we are looking forward to being able to use a full 5-dimensional PLR on the full exposure EFT analysis by taking these events into account for the first time. And so that's just those are a highlight of just a few results since Lux's WIMP search. There's been numerous publications on calibrations, on new microphysics, and new constraints on novel dark matter sources. We do have a few ongoing analyses still, despite LZ turning on in just a year. There's still plenty of physics to do with the data that we have with Lux. So I encourage people to check out Paul Terman's talk tomorrow, and I think it's the last talk of the day tomorrow on the lightly ionizing particle search. However, there is more to look forward to in 2021 from this, so please stay tuned. And I believe I'm close to out of time, so I'll probably just leave this up. But Lux has been, you know, a leader for the last decade, and we plan to continue doing physics and set limits into 2021, 15 years after the Lux was first formed. And even though not all of our results have been world-leading sensitivity limits, we have developed new techniques that will be invaluable for the next generation of multi-ton detectors. So with that, I'll conclude, and thank you, everyone. I appreciate your time.
Thank you, Greg. So we have the time for one question. You can either send it to me or just raise your hands. Okay, so thank you. Very interesting analysis. And so now we can go to my own collaboration with Alexander Kish, who will talk about the DarkSide experiment. So, Alexander.
Hello, I'm sharing my slides. Greetings from CERN, and welcome to my talk about dark matter searches with liquid argon detectors. In my talk, I will first cover DarkSide 50, a dual-phase TPC, and its latest physics results. Then I will present the status of DS20K experiment and associated developments and R&D that we're pursuing. After this, I will introduce global dark matter collaboration and the next phase of the experiment called ARGO. And finally, I will cover our very recent paper on coherent neutrino-nucleus scattering interaction and sensitivity of our future large argon detectors to core collapse supernova neutrinos. So I start with the DarkSide 50 experiment, which is coming to the end of its life at Laboratorio Nazionale del Gran Sasso, because it achieved all projected sensitivities. And here I explain a little bit its design. You can see a model here on the bottom left. And our largest structure is a stainless steel cylinder of 11-meter height and 10-meter diameter. It hosts 1 kiloton of ultra-pure water as a Cherenkov detector instrumented with the 88-inch photomultiplier tubes. So this Cherenkov detector serves as a passive shield for external radiation and as an active veto for muons. Inside this water tank, you can see a sphere with a diameter of 4 meters, and it contains 30 tons of boron-10 loaded liquid scintillator instrumented with 110 photomultiplier tubes. And this subsystem serves for active gamma and neutron veto, for active gamma reduction and active neutron veto. In the very middle of the liquid scintillator, you can see a cylinder also shown here, open on the bottom right. And this is the inner argon TPC with the 46 kilogram of liquid argon in the target. Here is a little bit more about the design of the actual TPC. So you can see here Teflon cylinder with 46 kilogram of argon inside. And you can also see here transparent anode and cathode. They are made out of fused silica and covered with the tetraphenylbutadiene for wavelength shifting. The whole volume is instrumented with 38 Hamamatsu PMTs, 3-inch diameter. And the PMTs are also instrumented with the specially developed cryogenic preamplifiers. So for this very low energy threshold and low background experiments, we cannot take any argon. That means we cannot take usual argon extracted from the atmosphere because it contains a lot of argon-39 radioactive isotopes created by cosmogenic activation of natural argon. So for the purpose of these experiments, we developed two plants, extraction and purification plants, in order to extract argon from underground. And this facility is called Urania and situated in the Colorado, United States. And this facility will allow us to extract from underground very clean argon without cosmogenic activation at the rate of 250 kilogram a day with a purity of 99.9%. Then we transport this very clean argon by ground and sea, so we cannot expose it again to cosmic rays, we cannot fly our gas. It will be transported to Sardinia, to another facility called Aria, where the distillation with the cryogenic column will take place. This will allow a factor of more than 1,000 separation between argon-40, that is actually used as detection media, and radioactive argon-39. And you can see here a picture of the first stage of the column called Cerrucci 1, and on the right, Cerrucci 2, which will be the height of the Eiffel Tower. In addition to depletion of argon, we will be able, with the distillation, to remove chemical impurities, also by a factor of about 1,000. So DarkSide 50 already performed a run with this underground argon, so the whole process has been tested. And you can see here on the right, the background spectrum measured with the atmospheric argon and put on the ground argon volume. And we achieved a separation factor of 1,400. So the total activity of underground argon of 0.7 millibecquerel per kilogram, this is very low activity. The detector was running with a light yield of 8 photoelectrons per keV and collected total exposure of about 16 ton days. So here also need to mention the plot on the bottom, and this basically the Y scale shows the fraction of light in the prompt fraction of light, and like this we can achieve very high pulse shape based discrimination of electromagnetic background of a factor of 10 to the 8, 10 to the 9, which is not possible with xenon detectors due to the nature of scintillation. And here you can see results on the right achieved with the underground run with DS50, which placed the WIMP nucleon on spin-independent cross-section to 10 to the minus 44 centimeters square. So besides this conventional WIMP search, several low-mass WIMP searches, dark matter searches, were performed with DarkSide 50 detector. And first here I describe low-mass WIMP search with ionization signal only. So we already heard numerous talks explaining the DPC technology. And basically in this analysis, we completely drop scintillation and we only detect proportional scintillation, which is proportional to the charge. So here the search is performed for low energy nuclear recoil signals. So we're talking here about WIMP mass range below 20 GeV. And the exposure used here was slightly lower in order to keep all parameters of the detector as constant as possible. So this analysis reports on about 6 ton days exposure. On the bottom left, you can see the spectrum in a number of collected measured electrons, also with the conversion to the electronic recoil scale and nuclear recoil scale. And our full signal acceptance here was 0.1 keV electronic recoil equivalent and analysis threshold set to 0.6 keV nuclear recoil equivalent. So this analysis, as you can see on the right, resulted in the best exclusion limit worldwide for light mass WIMPs with the masses between 1.8 and 6 GeV. You can see here some deviation of the depth curves. So there are two curves basically, and this is due to, as you can see here on the top insert, this is due to not sufficient knowledge of the absolute ionization yield for such low energy recoils. Another low mass dark matter search was performed for dark matter electron scattering. And here we're talking about searching not for a WIMP, but another dark matter candidate, which is very light and interacts through a vector mediator on a scale weaker than the weak scale. The analysis threshold here, so I also put here a link to quite some papers with numerous candidates that could fall under this light dark matter. And with the analysis threshold set to 3 extracted electrons, you can see again spectra here, which corresponds to 0.05 keV electronic recoil equivalent. We were able to achieve improvement upon existing limits for momentum-independent scattering of dark matter particles in the range of 30 to 100 MeV. The plots here presented for 2 scenarios, and here kinematics comes into play. So for heavy mediator and for light mediator, xenon and argon might have different sensitivities. So what is natural now, as I mentioned, DarkSide 50 experiment is coming to its end. What is natural for us is to think about a much larger experiment. And we are doing it by forming global argon dark matter collaboration, which joins the expertise of several argon dark matter experiments, such as DarkSide, DEEP, RDM, and MiniClean. So this collaboration includes more than 500 researchers from 83 institutions around the world and proceeding with the 2-step program. So the current step is the DarkSide 20K detector, or DS20K, which is projected to start at Laboratorio Nazionale del Gran Sasso from 2022. So this project will consist of a 50-ton underground argon dual-phase TPC enclosed in a 700-ton volume of atmospheric liquid argon. The plan of the experiment is to collect 100-ton U exposure utilizing 20-ton fiducial mass. Then the next stage after the DarkSide 20K is also already projected for 2029. And this is about 300-ton underground argon detector that will be hosted in SNOLAB. So the goals of the DarkSide 20K project is to increase sensitivity by 3 to 4 orders of magnitude with respect to DarkSide 50 by keeping the same total number of background events, so it's below 0.1 event per day kilogram. This obviously puts very stringent requirements in our experiment, and for this we need to have very low contamination in all structural components of the detector. We need to have very efficient shielding and neutron veto, and very important also is that we need special photosensors with a very reliable performance optimized to work in liquid argon at 87 Kelvin. So here are some curves, and you can see that DarkSide 20K will basically reach sensitivities of the order of xenon and ton and LZ, which we've already heard about today. And the final stage, argon, will surpass the sensitivity of the Darwin detector. Here's a little bit more about the design. So the big advantage and technological progress that allowed the development of such large-scale TPCs is using a membrane cryostat. This is, has numerous advantages due with respect to vacuum-insulated systems, because at this large scale, just very difficult to do. So this we see here. Also pictures of the already existing protodune cryostat, the inner side of it, and the model of the DarkSide 20K. Then inside we see in brown optical and electromagnetic radiation barrier. So it's made out of copper. Then inside we have shielding neutron veto. So this is the atmospheric argon volume that I mentioned of 700 ton. And it will also include gadolinium doped acrylic panels for neutron detection. Inside of the structure, you can see octagonal sealed acrylic TPC, which will host 50 ton of underground argon. And the whole volume will be instrumented with silicon photomultipliers for light detection with a total coverage of about 30 square meters. The detector is being prepared to be installed in Hall C at LNGS in Italy. And here you can see the very recent rendering of the entire hall. So here we can see the cryostat that I just mentioned with the TPC. next to it we can see clean room with the radon-free air and cryogenic test dewar. So in the installation and test will be performed here. Then on the other side we can see gas storage, cryogenic system and gas purification plant. And on top of the cryostat there is the data acquisition system. So as I mentioned, very important for us, since we detect light, to have very good and reliable photosensors. And the photosensor that the collaboration is planning to use is of the type NUV HD Cryo, which were developed in a combined effort by DarkSide members and so-called Fondazione Bruno Kessler, or FBK, in Trento, Italy. And here you can see some photos of the individual single photon avalanche diode with the very tiny devices with the area of about 30 square micrometer. Then these individual spots assembled into a single CPM, single photomultiplier, with the area of about 1 square centimeter. And the single photomultipliers then are assembled into a single photo detection module, and they consist of about 24. They consist of 24 individual photomultipliers. So the readout is performed the following way. There are called preamplifiers installed. So first the signal from each CPM is multiplied by factor of 4, and then summed, and then combined in this front-end electronic ports. So then we also, I'm talking about a photo detection module, which is basically it's a silicon photomultiplier tile plus front board electronics, and has the size of about 5 by 5 centimeter. You can see it in this picture with the one summed readout channel. And then these are assembled into a photo detection unit where 25 PDMs are hosted in the common mechanical support structure and basically represent the mechanical unit for DS20K detector. So this is the performance of these silicon photomultipliers. They're specially optimized to work on liquid argon temperature and have very high fill factor. The photo detection efficiency is better than those of photomultiplier tubes and is in the order of 50%. Also, these sensors feature very low dark count rate, and this you can see on the top plot, where you can see that also the performance surpasses the requirement.
Just to let you know,
Please say it again.
You have 5 minutes plus 5 minutes for questions.
Perfect, thank you. So here also there are some plots showing excellent photoelectron resolution, where we can distinguish single, double, triple photoelectron, and also very high signal-to-noise ratio above 20. So this the technology from FBK is being transferred to Alfoundry in Vezzano, Italy, where the raw silicon wafers will be produced, and then the mass production of the CPM-based photoelectronics will be happening at Gran Sasso in the so-called facility NOAA, and the tests will be performed in Naples. And here you can see some renderings and the photo of the lab. Then I mentioned that we'll have a neutron veto, and this is the 300-ton atmospheric argon inside this copper shell, separated by a plastic shell doped with gadolinium. So basically what happens that if there is a nuclear recall signal from a neutron inside the TPC, then this neutron will go into the gadolinium panel and produce a cascade of gamma photons, which are then detected with 3,000 photo detection units. This volume will also be instrumented with the specular reflector foils and PE and wavelength shifter opposite to TPB used in the TPC. So we can also imagine that measuring such low depletion factors of argon-39 is not easy. So the collaboration developed for this a special single-phase detector, which will be hosted at Canfranc laboratory inside the 1-ton RDM dual-phase detector, which will serve as a veto. And it will be able to measure depletion factor on the order of 2,000 with the precision of 10%. So we're also pursuing a prototyping program, and one prototype that performed the run already last year and unfortunately was stopped this year due to COVID is so-called proto-zero with the active volume of 10 kilogram. And here we test some basic things like conductive polymer for field cage and optimize the gas pocket. And next year, we're planning to run it with the two photo detection units on the top and bottom and perform for further studies. Second prototype will be running from next year. And this will happen at CERN. So this will have active volume of about 350 kilo and will contain 250 photo detection channels. You can see here a rendering of this prototype. Our technician lowering the inner cryostat into the outer one, and the installation at CERN Cryolab, also featuring underground cryogenic system with the very high cooling power, and that will allow very high circulation rates. So then very briefly, these very big detectors will allow us to do more than just dark matter searches. And for example, we're interested in detecting possible neutrinos from supernova explosions. So as we see, this kind of events release enormous amount of energy, and most of it goes into neutrinos. So neutrinos are ideal for studying final stages of stellar evolution and can provide constraints of the neutrino mass and ordering. And this is demonstrated by this plot, where we can see that both DarkSide and Argo will have a potential to discover supernova burst both throughout our galaxy and up to small Magellanic Cloud, and will be able to constrain the mean and total neutrino energy with the precision of about 10 to 30%, depending if it's DarkSide 20K and Argo. So here I stop on the summary slide, and I will not go through it, and I welcome your questions here.
Thank you for the nice talk. So we have a few minutes for questions. You can either raise your hand or send it in the chat. So, okay, so let's thank the speaker and thank you. And we'll go to the next talk with Tessio Melo about, so Tessio.
So can you see the slides?
Yeah, we can see you, not your slides now. Did you share it?
Oh, let me. Oh.
Okay, yes, now we can see. Thank you. Tessio will talk about the anomaly on Xenon 110 and about the light Z prime. So go ahead, thank you.
So first, I'd like to thank the organizers for giving me the opportunity to give this talk. My name is Tessio Melo. I'm from the International Institute of Physics in Natal. And I'm going to talk about this Xenon 110 anomaly, which was discussed in another talk this morning from the team. And I will present a model in which we try to explain this excess, but not with a dark matter particle, but rather with new neutrino interactions via light Z prime gauge boson. So this presentation is based on these two papers, which were done in collaboration with Manfred Linde, Ian Lombrini, and Farinaldo Queiroz. This paper is from this year, came after the announcement of the Xenon collaboration result. And this one is a bit older, is the one in which we first introduced this model. So, yeah, so the Xenon detector is this dual phase TPC, as explained in the previous talks. Cannot talk about that, but just to emphasize here that the important thing for us is that the Xenon is able to measure this scintillation and ionization signals, which enables one to discriminate between the nuclear and electronic recoils. So if you look at this S2 versus S1 plane, one is able to differentiate a band for nuclear recoils and another band for electronic recoils. So in this electronic band, it was expected around 230 events, and it was observed 285 events in this region between 1 and 7 kV. So this means an excess of 3.5 sigma of statistical significance. And what can be the cause of this excess? So it can be many things. It can be just a background that was not taken into account in the analysis, or just a statistical fluke. We can never discard this possibility. But we hope this is a genuine new physics signal. So this is not the kind of signal one I would expect from a dark matter particle, at least the typical dark matter scenario. So we decided to look at other directions. And one thing that it's important to notice is that the excess didn't appear at some random place in the spectrum, but it is localized towards the lower end of the spectrum, near the detector threshold. And this is interesting because there are some new physics scenarios in which an enhancement in the cross-section is expected at low energies, but it is not detected just because it is cut off by the detector threshold. So what Xenon might be seeing is a signal of this kind of new physics. And this is precisely what happens with neutron-electron elastic scattering mediated by a new vector boson. If the mass of this vector boson is very small, and small here means small compared to the electron mass. So in this case, the cross-section has this behavior. It goes as 1 over E squared, what is the electronic recoil energy. And this kind of interaction is enough to explain the Xenon anomaly. So this is the scenario we are considering here. The solar neutrinos hit the detectors interacting with electrons via this new Z-prime gauge boson. So the U1 symmetry, which is associated to this new vector boson, in our model is motivated by other regions. So we have a 2 Higgs doublet model in which there is a problem that is that the presence of new extra scalars mediate flavor changing processes at true level. And this is a problem because this kind of process is very well measured, and there are strong constraints coming from flavor experiments. So we'd like to avoid these couplings at true level, and for that reason we impose this U1 symmetry. And consequently we have this new gauge boson. So their interactions will be controlled by 3 parameters: the gauge coupling constant, the kinetic mixing, and the mass mixing, because of the doublets are charged under this new U1 symmetry. But in order to explain the anomaly, we are going to use only the first 2 parameters. And so we are ignoring the mass mixing. So there are a few possible charge assignments for the particles under this new symmetry. And we focus on the B minus L charge assignment. So in this case, the scattering cross-section has this form, which displays this 1 over E squared behavior at low energies. So we plot here this cross-section for some values of the Z prime mass. As you can see, for Z prime of 10 kV, there is this enhancement, very explicit. But if you increase the Z prime mass, this enhancement vanishes. For a mass of 500 kV, there is not enhancement at all. So we need this Z prime be very light. And to compare our predictions with the experimental data, we compute this differential weight, taking into account the solar neutrino flux. Only the neutrinos that come from the PP chain and the beryllium-7 line contribute significantly to the recoil events at Xenon detector. We checked that we were able to reproduce the expected neutrino background. And then we performed a chi-square fit in the range between 1 and 30 kV of the electronic recoil energies. And here's the result. So this plot we showed, this green band is the favored region to explain to reproduce the excess in this coupling versus MZ prime plane. So we need couplings of order 10 to the minus 6 and masses, as you can see, always below 100 kV. Here we have the same kind of plot in the plane MZ prime kinetic mixing. The kinetic mixing is of order 10 to the minus 5. And finally, we show here some sample signals for different values of the Z prime mass, along with the experimental data. As you can see here, the lower the Z prime mass, we get a higher peak. And as we increase this mass, the peak gets dwindled. But we have here a range of masses possible to explain this anomaly. So I leave here my conclusions and I stop here. Thank you.
Thank you, Tessio. I didn't interrupt you because I saw you were on time, so thank you very much for that. So we have a question from Malcolm Ferran. Do you want to make it yourself? You can just turn on the speaker.
Hi, thank you. Can you hear me?
Yes.
Can you comment on constraints on your model from helium burning stars and supernovae?
Yes, so there are these astrophysical bounds on this light Z prime for masses below 1 MeV. And we considered here mostly lab-based constraints because these astrophysical bounds can be avoided if we have environmental effects involving the Z prime. So there are some papers that question the robustness of these astrophysical bounds, but it's a fact that for these values of Z prime mass, it's in tension with these astrophysical bounds, but they can be avoided with environment effects. But we checked the lab-based bounds and it fulfilled all of them.
Okay, thank you.
Okay, just continuing the bounds for the Z prime. I wonder, so do you have, like, what's the range of your Z prime? Are there other bounds that don't come from the helium burning stars and supernova? Or can it be anything?
So can you repeat, please, the question?
Mainly, if do you have any range for the Z prime? Because you say you can avoid the constraints that were just mentioned. But in your model, do you have a range for the Z prime?
In the mass, you're talking
Yes, in the
mass?
mass, yes.
Yeah. So no, for this mass, the astrophysical bounds, it's intention with the astrophysical bounds. We cannot change the mass of the Z prime. So what can be done is you can consider new interactions of the Z prime inside the stellar environment. And this environment can effectively change the mass of the Z prime and make it heavier. So this avoid the stellar cooling and so on.
But then it won't be able to explain the excess because it goes to the heavier side. Just.
Thank you very much. I will tell you a little bit about a few new things we've done on nonlinear stuff.
And the Z prime remains light. Okay, but we didn't dig on these details in astrophysical environments.
Scales are called dark matter.
Okay, thank you. So I guess we got to
this figure
to the end of this talk. Let's go to the last talk of this section with Leonardo Pérez.
To be aware when we talk about
thank you once again, Tessio.
A new class of galaxies that were first called like this in 2000.
Are you hearing me now? Good morning.
Yes, yes, we see you. You can share your screen now.
Okay.
Yes, so Leonardo will talk about boosted dark matter on large TPC experiments. Okay, thank you. Yes. You can start.
Okay, so first of all, thank you to the organizers. My name is Leonardo Pérez. I'm a master student at the Federal University of Rio de Janeiro. And as I said, I want to talk about boosted dark matter in larger TPC experiments. So boosted dark matter is a class of dark matter models that hypothesizes a multi-component dark sector in which there is a relic abundant that I'm going to call psi, which preserves the WIMP paradigm. And in the later times of the universe, it can annihilate and produce the other components of the dark sector, which I'm going to call Chi, that receives a boost due to the mass difference between the particles. So I'm going to explore, they are very manipulated model, but I'm going to explain just the annihilation process. And so the annihilation process can occur in regions of dense concentration of dark matter, such as the galaxy center or the sun. I'm going to focus here the annihilation process in the sun. And it's hypothesized also that the Chi component of the dark sector, the boosted dark matter, can interact with electrons and nucleons, while the psi can't. So the focus of the presentation will be in boosted dark matter produced by annihilation in the sun and the detector of large TPC experiments like June. First of all, I would like to say that this is not of June's official talk, but I would like to talk about June. There is a international experiment for neutrino science and proton decay studies, which is under construction right now in the US, and it is basically made by it's a very short description. A neutrino being hosted in Fermilab, and then large detectors of liquid argon put more than 1,000 kilometers in South Dakota underground. So it is expected that June gonna have a low detection threshold, so they're gonna be the ideal candidates to conduct this search for boosted dark matter in the way that we are exploring here. I think that much of all we'll talk about the TPC technology here. So I'm gonna just explain very fast. This is a single phase, what we call single phase, which the incoming neutron particle, when interacts in the detector, produces final state particles charged, and they ionize the medium, which is liquid argon, and the electrons are drifted to wires and produce electric ripples, so making possible the spatial reconstruction of the event, and also light detectors are added to determine the event time. With that, you can reconstruct the 3D event in the detector. It's very beautiful. I'm sure that many of you have looked some plots of reconstruction event in RTPC. So as I said, they offer a low detection threshold for hadrons, and in general, they are very good, as we saw here in many talks. They are a very good opportunity to study physics beyond the standard model. This is the paper that I'm going to continue the work. It was made by these collaborators, and this paper lays the foundations to search the boosted dark matter hadronic interactions in doing experiments that come from the sun. So the focus of the work, it was only about elastic scattering and deep inelastic scattering, and the detector target nucleus argon, of course. And the interactions are hypothesized to be mediated by a Z-prime vector boson, which is a neutral current-like event. And we are, as I said, we are taking advantage here of large TPC for only search for hadronic channels. So here in the right, this is what we expect for signal. We expect boosted dark matter particle that is created by annihilation in the sun and interacts in our detector. And here we have the below we have the main background, which is atmospheric neutrinos that mimic the boosted dark matter interaction. So this was here in the equation, it was the benchmark model for the Lagrangian usage in this model. The coupling strength GZ prime is the same even for the annihilation process as so for the dark matter standard model interaction, which is this is a simplistic assumption, right? Just to start. And the GP is the current that has scale components for dark matter and axial current for quarks. And this is our three parameters here, the mass of psi, the mass of chi, and the gamma and the Lorentz factor. So if you set 2, you can, the third one is already defined. So you're gonna use the chi mass and the Lorentz factor. So as I said, the main background is atmospheric neutrino neutral current interactions.
Leonardo, you have 2 minutes plus 2 minutes for questions.
Okay, I'll go quickly. I'm all right. So this is like from the paper. It shows how boosted dark matter can overcome the background expected signal, and for larger Lorentz boost, the main goal in the paper was to prove the coupling constant and evaluate the sensitivity of the detector for this hypothesized particle, and we use it a single variate analysis. There is an angular curve since we expect that the background should have a flat distribution, while the boost dark matter signal is aligned with the sun direction, which is shown in this plot. And here we can see that Dune will be able to improve sensibilities, especially in lower energies compared to other neutrino experiments. So I'm going to talk about in this quick end of what I'm doing here. So all the work was done with a parameterized detector resolution, right? So my job here is to do a new analysis, make a new analysis, and with a realistic detector simulation and reconstruct for signal and background. So we are usually in this initial stage here, which is reproduced by a Gini model generator, the interaction and the fine state particles. We pretend to use after that adjunct to propagate the particles in the medium. And then we simulate the detector response in Dune. And after that, we select signals using reconstructed event kinematics, particle IDs to perform the statistical analysis. So this is the final analysis that we are interested to determine the sensitivity of the experiment, right? And this is the previous, the first results that we are checking the validation of the signal samples at truth level. I'm doing this analysis in collaboration with Josh Berger, Gianluca Petrillo, Ion Tessai, and my advisor here in Rio, João de Melo Neto. And we are testing the impact of different models of nuclear effects and collaborating with Dune nuclear on the K group, which is doing similar things. So you can hear here, we can see here that the incoming dark matter particle momentum, and after the interaction, there is a distribution against this validation of the signal samples. Here we can see how the dark matter behaves after the interaction concerning to the angle related to the sun. So there is a very small deviation here. So that you can see in this scale. And one of the new features of this analysis that we are using, I spread the interactions in Dune's framework. So we are actually doing Dune's detector array to expect the interactions in the detector, and the geographical location of Dune was also used in the simulation. So you can see here the last plot, which is the distribution of the incident dark matter particle in the coordinates of the detector. So I have many job to do in next month, in the next year. So thank you very much. I hope that I hope I have some time to question.
Okay, thank you. We just, finished right on time. So I will ask everybody if they have any questions to direct them straight to the speaker from all the sessions. And I would like to thank everyone who spoke in the direct detection session. They were all very good talks. Thank you. And now we have a 5 minutes break. So thanks to all of you.
Thank you.
So,
thank you.
Thank you very much. While thanking all the speakers of this session, once again, maybe Enrico, you want to set up the...
It's almost done. I'm almost done with all of them. I would just ask to the speakers which are here already co-hosts to share their screen so that we can quickly check if everything is working. So maybe we can go in order. Malcolm,